was beginning to think it would be a one-on-one session, Elijah.
Oh, Carson's here too. Can't forget him.
Oh yeah, okay. He doesn't have his camera on yet. Are you guys roommates?
No, not that I know of.
Yeah, for just a second when you said here, I thought maybe in the same apartment or same office or whatever.
Oh no, no,
My
just
mistake.
in this Zoom call.
Virtually here.
Hmm.
All right, well, we are in November now. Everybody survived Halloween evening, I suppose. That's good. My blood sugar is still in the 200s after having all the candy that my kids didn't want. All right. I had office hours yesterday. Nobody showed up. I'm available tomorrow. I've got a few things going on, but if you find yourself in need of some help on the homework that's due tomorrow afternoon, feel free to reach out to me. Next week, don't forget Tuesday is reading day for us, so we won't have any formal class that day. But I'll have office hours. I'll make my office hours again on Wednesday next week from 1 to 2:30. And I actually have a faculty meeting then, so I might need to modify that a little bit. But then I'll also have office hours sometime on Thursday as well. I'll figure out when those are and update that for you guys. Review of our due dates. You guys have some first order analysis due tomorrow afternoon. And then you also have a matrix frame analysis due next Friday. And so that's brings us to our agenda for today, and that is to look at the matrix analysis of frames. And if you are following along on Canvas, I had posted the matrix analysis PDF earlier this morning, about 9 or 9:30, somewhere thereabouts. And then after I was going through that, preparing for class, it occurred to me that we might get through that in less than 60 minutes. So just about 10 minutes ago, I posted another PDF of a second presentation. So I don't know if we'll get to that today or not, but I didn't want to waste 15 minutes if we were to finish early. So with that, let's go ahead and jump into our discussion of matrix analysis of frames. All right, so this is the fifth of 5 lectures that I have on matrix analysis for this class. And I think that I open up, excuse me, just about all 5 of them with basically the same slide. The direct stiffness method revolves around the creation or the assembly of a global stiffness matrix. We have displacements in the structure that correspond to the degrees of freedom that we identify. And then we have externally applied loads that we consider in the solution. So the process is to solve for the unknown displacements. And basically, we're taking this series of matrix operations, the stiffness matrix K times the unknown displacements delta is equal to P. And we can go through a series of linear algebra to solve for the unknown displacements delta. So overall goal is to develop a set of simultaneous equations that our computer can solve. So in previous lectures, we had addressed a truss element, the modeling of trusses. Sorry, I'm jumping over my words. I haven't spoke much today. I've been working on some other stuff, and I should warm up like a singer or something maybe. We first went through and derived the stiffness matrix for the truss elements in our global coordinates. So the degrees of freedom at each end are parallel to our global X and global Y axes. In a later presentation, I think it was number 3, we derived the element stiffness matrix in our local coordinate system and then used pre and post multiplication to transform or to convert that local element stiffness to a global element stiffness before we assemble it. And then in our 4th lecture on matrix analysis, we addressed beam elements, and we considered beam elements with 2 degrees of freedom at each end, one that's translational, perpendicular to the axis of the member, and the other that is rotational. So we have flexure and shear that we were considering. And we did that with the elements aligned parallel to a global x-axis. But it works out that these stiffness matrices are appropriate both in local or global coordinates because we had our local coordinate system aligned parallel to our global coordinate system. Now we could rotate that if we wanted to, and we could look at our beam element aligned in with some angle relative to the x-axis, and then that stiffness matrix that we were using for beam analysis then becomes the stiffness in the beam local coordinate system. And so the process for deriving the beam stiffness in global coordinates would be the pre and post multiplication procedure that we use for trusses, but to this point it hasn't been necessary to do that. Excuse me. All right, so what we're going to do is we're going to take the lessons that we learned in the context of the truss and the lessons that we learned in the context of the beam, and we're going to combine them together. When we talked about this in the context of a frame, we end up with 3 degrees of freedom at each end of our element. We have 2 translational and 1 rotational. 1 translational in local coordinates corresponds to an axial force. The other corresponds to a shear force. And then, of course, you have the end moments that are represented by theta in this case. So if we go and look at the 2 stiffness matrices that we have, the one that's shown up here at the top is our stiffness matrix from our beam element. The one that's at the bottom is the stiffness matrix that we had from our truss element, both in local coordinate systems. What you can see is that we have all 6 degrees of freedom represented with those 2 stiffness matrices. And all that we need to do is overlap them or merge them or combine them in some way so that we have one element stiffness matrix that accommodates all 6 degrees of freedom. And so what I've done is I've identified those degrees of freedom shown here in blue. And what you can see is that in some cases, we actually have common degrees of freedom. So we have this value of theta sub y at the ith end. We have this value of theta sub y at the jth end. And luckily for us, in the truss element stiffness matrix, those columns and the rows that correspond to them are all zeros. So when we go and add these 2 matrices together or combine them so that we can consider frame stiffness, then it works out to be a trivial operation. And so when we do that, we end up with a 6x6 stiffness matrix that characterizes the behavior of a frame element in 2 dimensions. Now, if we were to go in 3 dimensions, it would get a lot more complicated. Each of these elements would be 12 by 12. You would have 3 translational and 3 rotational degrees of freedom at each end of every member. We're not going to do that. I think that going to this extent where we're looking at a 2-dimensional frame is sufficient to illustrate what we need to for this class. Remember, this class isn't a class on matrix analysis, even though you might think that I don't know that. But we're doing what I think is enough matrix analysis to give you more insight into the inner operations of programs like visual analysis in SAP 2000. So this little exercise is basically what constitutes the discussion of a frame analysis. So after you have this element stiffness matrix in local coordinates, everything else in the analysis of a 2-dimensional frame is just a slight modification of operations that we've already performed. When you went through and did the second analysis homework, you used pre and post multiplication to develop a stiffness matrix for a truss. And we're going to do that here because we have our stiffness matrix is given to us only in local coordinates. It's possible to get a stiffness matrix for frame elements in global coordinates directly, but that matrix then becomes very large. Each of the elements has at least 3 different terms. You have a stiffness term, a shear term, and a moment term in each one of them. And so it's algebraically complex enough that it becomes easier to pre and post multiply than it is to actually work with the stiffness matrix in global coordinates. So the rotation matrix that we use for this is a little bit different, though. When we looked at this in the context of truss elements, we just had a 4x4 rotation matrix or 4x4 transformation matrix, gamma. When we look at transforming 2 different coordinate systems in 2 dimensions, it works out that transforming that rotational degree of freedom is trivial. It's the same rotation in one local coordinate system as it is in the other global coordinate system. So if we come in and look at our global coordinate system like this, you have a capital X, a capital Y coordinate system, and then compare that to a local coordinate system that's like this, where I'm going to use a lowercase x and a lowercase y axis. Then when we consider a rotation, that rotation is the same regardless of whether you look at it within the context of the global coordinate system or the local coordinate system. So because of that, you just end up with a 1 on the diagonal of the rotation matrix that corresponds to that rotational degree of freedom. So when we do our matrix assembly, the first step is to take our frame element stiffness matrix and then pre and post multiply by that transformation matrix gamma. Okay. Then if you find yourself, let me go back a slide, make sure. Yeah. If you find yourself with a case where you have a release at the ith end, then so it's might not jump right out at you. We have a pin connecting the ith end of the member to that first node. Then you end up with a stiffness matrix that looks like this, where we have a column of zeros and a row of zeros corresponding to the third degree of freedom. And when you look at the case where you have a rotational release or a moment release at the second end of the member, then you end up with a column of zeros and a row of zeros there. Now, one thing to bear in mind, I've had this conversation with a couple of you already, is that it's not as simple as just zeroing out the column and the row that correspond to that released degree of freedom. If we go in here and look at this, take a look, for example, at this coefficient here, 3EI over L. Or you go back and look at this coefficient here, 3EI over L. If we look at the element stiffness matrix without any releases, then that coefficient changes to a 12EI over L, right? And so it's not just that one row and that one column that change, it's other coefficients within that matrix change as well. I should have done a better job pointing that out when we went through this lecture a few weeks ago, because that's a mistake that I made too when I was going through this the first time. I thought, oh, we just put zeros in and life is good and everybody gets the right answer. But no, it doesn't work that way. So, all right. So yeah, now that we have an element stiffness matrix for a frame element in 2 dimensions, we can go through and do an analysis. And so what I'm going to do is take this problem here. I'll stop short of saying I'm going to solve it, but I'll go through the process that we would use to solve this problem. Now, I have a to-do list of things I'd like to improve on most of my classes, and this example is one of those. I'm not real fond of this example. When I created this some years ago, I was teaching, I think, basic strength of materials at the same time. And so I was looking for something with a goofy load in an odd direction. And so I picked this problem and I thought, oh, it'll be great. It's in metric, SI units. And I suppose that's nice that we can solve a problem in metric, but I'm not particularly fond of this. But anyways, that being said, let's go ahead and move on. So I'm to give some shape to all the members. I'm going to use a W530 by 66. So that's 530 millimeters deep and 66 kilograms per meter, I think is the way that works. Our modulus of elasticity, assuming steel, is 200 gigapascals. We have a force F at, I guess that's node A, B, C, D. That's going to be 1.2 kilonewtons acting to the left. And then we have a distributed load on our inclined member number 1, that's 1.5 meters acting perpendicular to the axis of that member. So when I go through this, I'm going to have to consider that I have a release. Now, this is worth talking about. So I have a pin down here, and I have a pin up here. And so the pin at A doesn't have to be treated like a release. That can be a regular end of a member that just does not have a rotational restraint to it. It doesn't have a rotational support. So no release is required at A. However, we're going to need a release at node C. It's either going to have to be a release between the right end of member 1 or the left end of member 2, but not both. And so I want to call that out. Sometimes students will see this and say, well, gee, I need a release here. and you don't. You just have a node that's connected to member one, and then that node is not restrained with a support condition indicating restraint of momentum. So I can't remember whether I release the right end of member one or the left end of member two. I think I'm going to release the left end of member two. And the reason why I think that is that when you go through and look at the equivalent end actions for member number one, we would need a different set of equivalent end actions if there was a release at the right end of that member than we would need if there isn't. And so it makes the calculation of the equivalent end actions simpler if we release the left end of member two, since it's not loaded, than if we release the right end of member number one. Now I'll probably get 3 slides ahead and then find out I did it the other way, just because that's the way life goes. So here are the degrees of freedom that I'm going to identify. So I've got degree of freedom 1, 2, and 3 at node A, 4, 5, and 6 at node B, 7, 8, and 9 at node C, at node D, I guess, and then 10, 11, 12 at node B. So in this case, I'm not necessarily numbering them, the degrees of freedom, the same way that I would label the nodes. That's pretty good though, because the way that I have these numbered, the members connect the degrees of freedom to give us the least bandwidth on our stiffness matrix, and that's going to keep the problem a little bit easier to solve. But that's just a consequence of the unique geometry of this frame. You can't do that for all frames, obviously. All right, so I'm going to go through and look at each one of these element stiffness matrices. Here's my element stiffness matrix corresponding to member number one, and then the rotation matrix for element number one. And I can see here that I did not release element number one because there is not a column or row of zeros in this. None of the rows or columns are completely zeros, so there is no release there. So if I go through and do my pre and post multiplication using this rotation matrix gamma and this stiffness matrix in local coordinates k, then I end up with this stiffness matrix in global coordinates k1. All right, now I can do the same thing with element stiffness number two. And so here you can see that I do have that release implemented here. I have the third column and the third row are set equal to 0. And then the coefficients on the other stiffness terms are modified appropriately. So this particular element is aligned such that its local x-axis is parallel to the global x-axis. So when you look at the transformation matrix gamma, it's basically just an identity matrix, right? It has diagonal terms are all 1, but everything else is equal to 0. So there's technically no transformation required at all. The local K2 matrix is going to be the same as the global K2 matrix. All right, then finally, when I look at the third element, then here's my element stiffness in local coordinates, and then my transformation matrix gamma. And so the way that this works out, let me go ahead and sketch on here. I'll do it in black and blue again. We have a global stiffness, global coordinate system that looks like that. And we have a local coordinate system that looks like this. So that's the local X. This is the local Y. And so when you look at the transformation matrix, you can see that reflected, right? The local excuse me, the local x-axis acts in the same as the global y. The local y-axis acts in the opposite of the global x-axis. So you end up with a 1 and a negative 1. And then, of course, that rotation is going to be the same. So that diagonal term is there. And so if you're once you get through a number of these example problems, you can kind of look at the transformation matrix sometimes and see how the member is oriented just by the way that those degrees of freedom are mapped between one coordinate system and the other. So we go through the pre and the post multiplication process, and we end up with that. So now we have a stiffness matrix for elements 1, 2, and 3, all in our global coordinate system. And so now the next step would be to augment each of those, take each of those from a 6 by 6 element stiffness matrix to a 12 by 12 global stiffness matrix, and then add them together so that we complete the assembly process, and we end up with that as our unrestrained global stiffness matrix, right? So we have 12 degrees of freedom, and so that's a 12 by 12 matrix. Excuse me. Now, the next thing that I'll do is I'll go through the process of shaking out the loads, determining the loads. And so for this particular problem, I have two loads, and they're two different types. I have the loading on member number one. That's a member load. So I'm going to need to develop equivalent end actions for that. And then I have the nodal load up there at joint D. And so that force F is going to be a nodal load. So I'm going to have one nodal load. I'm going to have one member load, one set of equivalent end actions. So let's go through that process. And so if I go through and look at that, I can develop these member loads and local coordinates. So this is a new wrinkle. When we developed equivalent end actions in the past, they were always for beams, and we never had to transform the equivalent end actions from a local coordinate system to a global coordinate system. So this is a new step. So what I'm going to do is I'm going to develop the equivalent end actions for member number one in the local coordinates. And so I can do that by recognizing that the axial force corresponding to degree of freedom 1 and degree of freedom 4 is going to be equal to 0. Excuse me. Then I can develop the end shears corresponding to degree of freedom 2 and 5. That's going to be equal to 0.3 kilonewtons. But as an equivalent end action, that equivalent force actually acts in the opposite direction of what I'm showing as positive. So the equivalent end action, I think I have it drawn in on a slide coming up here, is actually acting in that direction, right? So that green vector is equivalent to the red distributed load. And then we have the equivalent end actions corresponding to the moments at the ends of the member. So we have WL squared over 8, or 112.5 kilonewton millimeters. And so that equivalent end action is going like this at the left end and going like that at the right end. So I end up with a negative value here, but a positive value there. Okay, now we can go through, and when I taught this the last time, I was using this to emphasize the equivalent end action process. And so we can go through and look at this. That's a snip from the Purdue FE fixed end moments, and I like that that particular handout a lot. So that's the way I do that. And so what I'm showing here are the equivalent end actions. And so these are the fixed end actions that are shown here on this slide. And so these are basically the reactions to the loading that's on that element. Joe, you might want to tell Dr. Rosati that you're in class right now and that he shouldn't be disturbing you. What we're going to develop from those fixed end actions are the equivalent end actions. And that's why I'm distinguishing here. Hopefully nobody's colorblind. Sometimes I get a student who can't see green, and that's problematic. Right. And so I was emphasizing the differences in the signs when I created this series of slides before. So we take these equivalent end actions and we develop from that the excuse me, the load matrix that's going to come from that, right? So that's where the plus and the minus signs come from. All right, so we're going to take those values. Those are the equivalent end actions that we have. We put them in a form of a matrix. We have our equivalent end actions in local coordinates here. We multiply by, pre-multiply by the transpose of gamma, and we get the equivalent end actions in global coordinates. And so we're basically transforming from one coordinate system to another. And so what you can see is we have 0 axial force and degrees of freedom 1 and 4. But when we transform, that corresponds to some equivalent end action that is in the x direction. We also have some portion of that shear that corresponds to local degrees of freedom 2 and 5, and they correspond to a load that acts in the y direction. And then that rotation just translates directly. It's a one-to-one translation there. So what I can do then is I have my member loads that are shown here. So these are the member forces, and you can see that they act only on degrees of freedom 1 through 6. Here are my nodal loads or joint loads, and that acts only corresponding to degree of freedom number 7. So I add these two together to get my total load matrix P. And then I can start the process of reordering the degrees of freedom, subdividing or partitioning that matrix, and then going through the solution process. And so what I've done is I've reordered it so the unrestrained degrees of freedom are first and the restrained degrees of freedom are second. So let me go back and let's look at the model again. So I have pin support at A, a pin support at B. So when I go through and look at the degrees of freedom 1 and 2 are restrained, degrees of freedom 10 and 11 are restrained, but everything else is unrestrained. So let's go back here. And so you can see that's how I've reordered things. Degrees of freedom 1, 2, 10, and 11 are at the end of this, right? And so we can go through our matrix solution process. We can develop the reaction forces that we have, both the net and then accommodating the equivalent end actions. We get the total reactions at the end. Then we can solve for our end actions and come up with our member end forces. And so with the end forces that come in from member number 1, I think this is member number 1, we can solve for the pin force. And so I have these values here, 0.3 kilonewtons and 0 kilonewtons. So I can take the square root of the sum of the squares and solve for that force that's in that pin. All right, so with that, you guys should be positioned to where you can tackle the homework that corresponds to the matrix analysis. I've forgotten which homework assignment that is. I'm going to go look on Canvas now. Let's get rid of that in a hurry. Nobody wants to talk politics nowadays. I'd probably be brought up on charges just for showing CNN. Should be if I'm All right, let's look at the assignments that we have here. So if we look, matrix analysis of a portal frame. So let's click here for the assignment and see what it is that we have. There we go. Yep. So a 2-bay single story portal frame. So you have 1, 2, 3, 4, 5 elements. You have 6 nodes. So you're going to end up with an 18 by 18 stiffness matrix with 1, 2, 3, 4, 5, 6, 7, 8 degrees of freedom restrained. And so if you go through and look at the degrees of freedom, then degrees of freedom 1, 2, and 3 are restrained. Degrees of freedom 10 and 11 are restrained. And degrees of freedom 16, 17, and 18 are restrained. You'll have to develop equivalent end actions for members 2 and 4. And then you have nodal loads at nodes 2, 3, and 5. It looks like with this particular situation, you won't have to do any pre or post multiplication with your equivalent end actions because the members that have member loads are all in the same coordinates, are all parallel to the x-axis. So you don't have to do any pre or post multiplication on that. All right, and then here's some report the horizontal displacements at nodes 2, 3, and 5, report the maximum minimum shear forces and bending moments for each member, and then sketch the shear force and bending moment diagrams for all the members as well. So have fun with that. I expect that if you guys work through the previous matrix analysis homeworks on your own, and or maybe you did due diligence on that this will probably take something on the order of 2 to 3 hours to complete. I doubt that you get it right the first time, but don't forget that you can model this in visual analysis and compare the results that you get from your matrix analysis to the visual analysis results, and so you can check your answers. You don't have to guess as to whether everything is right or not. All right, so with that, questions? Yeah, that's this kind of thing where you don't know what questions you're going to have until you dig into the homework. All right. I'm glad I posted that other, because like I mentioned in my steel design class yesterday, I'm not a really great judge of how much time something is going to take when I make a presentation. If I'm doing it at a conference or something like that, then I'll rehearse and I'll know, but I don't rehearse these before class. I go through them, so I have a general idea what I'm going to cover, but I don't actually rehearse the presentation. All right, so our next step is going to be second order analysis. And if you go through and look at the assignments, actually, the assignment number 9 is actually going back and doing some second order analysis. So we don't know what a second order analysis is, but you will in a few minutes, right? So let's go through with some terminology. And we've been doing a lot of analyses in this class, and you guys have done a lot of analyses by hand in CVE 3001 or the equivalent analysis class that you took in your during your undergraduate work. And the first order analysis is an analysis which is based on the undeformed geometry of the structure. So we all know that when you put a load on a beam or you put a load on a portal frame, it's going to cause that frame or that beam to displace or to deform, to deflect is a better word probably. We base the equilibrium conditions of our calculations, however, on the undeflected geometry. A second order analysis, in contrast to that, is one where we base the equilibrium conditions on the deformed structure. So we calculate equilibrium at every one of the nodes based on the final position of those nodes. And then that gives us a slightly different answer in a lot of cases than what we would get with a first order analysis. Now, the problem with this is that the amount of deformation is a function of the equilibrium conditions, but the equilibrium conditions are a function of the deformation. So you end up with a problem that is inherently iterative in nature. You know, the end result is dependent upon the parameters that go into it. So you have to iterate, or you have to come up with some kind of a process in order to come to a final solution. Now, when we look at the deformations, we account for them in two different ways. We have what is called a P big delta effect, and we have a P little delta effect. The P big delta effect is an effect of the loads that are acting on the displaced location of the nodes or the joints within our structure. And a P little delta effect is an effect that is related to the loads that are acting on the deflected shape of a member. So when you see a P big delta, we're talking about nodal displacements within our structure. If you see a P little delta, we're talking about member displacements. How much does a member deflect in between its ends, as opposed to how much the ends of the member itself deflect. And then there's a more general term. A nonlinear analysis is more general than a second order analysis. Second order analysis just alludes to the idea that we're accounting for deformations of the structure. When we talk about a nonlinear analysis, it could be either deformations of the structure, or we could be talking about yielding of the material, or nonlinear material behavior that's included in there. And so when you go in and do a second order nonlinear analysis, you're accounting for one where you're accounting for the geometric deformations, and you're accounting for the possibility of yielding or some type of failure of the material itself. So this is a classic example of a second order problem. You know, this or variations of this are often used to illustrate what the problem is and how we account for it. So let's take a look at this. We have a cantilever column. So it's fixed at a base at point A. It's free up at the top at point B. We're going to apply a vertical force 200 kips, and we're going to apply a lateral load of 20 kips. So we can go through and do some rudimentary analysis of this. If we take the sum of the moments at point A, we end up with a base moment equal to 3,600 kip inches. We can also predict what the displacement at the top of that column is going to be. So it's going to displace to the right by an amount roughly equal to HL cubed divided by 3EI. So you might be used to seeing the beam arranged horizontally. If you have like a cantilever beam, it's PL cubed over 3EI. But in this case, that force is a horizontal force, so I'm calling it H instead of P. So we would expect a tip displacement of 1.342 inches. And so when we look at the way that this thing deflects, that's what we would expect. Now, if we were doing a first order analysis, we would be done. We would design the member for a moment of 3,600 kip inches. We would expect a tip displacement of 1.3 inches. And we would walk away and be done. And that would be our first order analysis. However, if we're going to do a second order analysis, we recognize that that tip B, the top of this member, has deflected to the right by 1.342 inches. So now, if we reconsider equilibrium of this column, the moment at the base is no longer just 3,600 kip inches. It's 3,600 kip inches plus that 200 kips acting eccentrically by an amount of 1.3 inches. So now the moment at the base of the column is 3,868 kip inches instead of 3,600 kip inches. We could also reevaluate the tip displacement. Now, since we have additional moment in the member along the length of the member, we can expect it to deflect even further. So if you look at that equation, delta is equal to HL cubed over 3EI plus a moment ML squared over 2EI. That's not strictly correct, but it's close enough for the purposes of our example problem here. And what you can see is that by having that load of 200 kips acting eccentrically, 1.342 inches, we get an increase in displacement at the top of 0.15 inches, right? So now the tip displacement goes from 1.342 to 1.492 inches. So that's not the end of the problem, though, right? And because now we have an additional displacement at the top of the column, now we have to reconsider equilibrium. And now the base moment goes from, let's see, what do we have here? 3,868 kip inches after our first iteration. Now, after our second iteration, we go from to 3,898, and our tip displacement goes to 1.509 inches. But now the tip is moved again. So we consider our third iteration. Now we end up with 3,902 kip inches at the base. We end up with a tip displacement of 1.511 inches at the top. But it keeps moving, so we keep doing this process. And eventually what we're going to find is that after we go through 2 subsequent iterations, hopefully the problem will converge to the point where we don't end up with any additional displacement. If we go through 2 or 3 different iterations, we find that the top actually moves, we end up with the same displacement at the end. All right, so we have a displacement here, 1.51 inches. It's the same as what we started with. And that represents a convergence of the problem, and we can stop our solution process and we could go forward and design with a moment at the base of 3,902 kip inches and expect a tip displacement 1.511 inches. These problems don't always converge. If you selected a member with a lower stiffness, a smaller beam section, for example, maybe that increase in the moment at the base would lead to a divergent solution where you actually end up with a collapse of the system instead of a convergence to a stable condition. All right, so we can go through and do hand calcs. I'm estimating that my first order analysis results in 3,600 kip inches, 1.3 inches of displacement. My second order analysis results in 3,900 kip inches or 1.5 inches of displacement. If we go through and do this same exercise in SAP 2000, the results that I get are slightly different, but comparable, right? The equation that I was using to calculate the tip displacement wasn't exactly correct. The moment in the beam, due to the eccentrically applied load, isn't uniform over the entire length. It gets smaller at the bottom as the eccentricity decreases a little bit. But you can see the process when we do it with the hand calculations is similar to what you would get out of SAP 2000. Now, oftentimes what we want to do is have a quantity that indicates to us how important the second order analysis is. In some structures, if the structure is very stiff and it's not going to displace very much, then the second order effects aren't very large, and sometimes we don't even need to worry about them. In other structures, however, structures that are more flexible, then the second order effects can be problematic, and we certainly have to consider those. And so the quantity that we use is often by taking the second order displacements divided by the first order displacements. So for this particular problem, if we take the second order displacement at the tip divided by the first order displacement at the tip, we end up with a value of 1.126 based on the hand calculations, or a value of 1.098 based on SAP 2000 calculations. And so that value of delta second divided by delta first is a measure of how much the second order effects are contributing to the final solution of the problem. General rule of thumb, if you're working per AISC, if you get a value that's greater than 1.1, then that's a case where those second order effects are large enough that you need to jump through some extra hoops. You need to go through some extra you have to go through a second order analysis in order to feel good about your design. There's some other values that trigger other things as well. If you get a value that's 1.5, then that structure is probably not stiff enough to be considered safe. If you have a value of 1.5, then you have to really go through a rigorous analysis to make sure that your structure is going to have a convergent solution and not a divergent solution that results in a collapse. Right? Now, the ironic thing here is that in order to know whether the second order effects are important or not, you have to do a second order analysis, right? In order to calculate that ratio of delta second to delta first, you have to have delta second. And so it's kind of laughable that, you go through that process, you say maybe you would come up with a value of delta second over delta first that's 1.05. And you could say, okay, I don't need to do a second order analysis because that number is small enough, but you've already done the second order analysis anyway. So I always kind of thought that was kind of funny. If we go through and do this with shear deformations included, then we get different numbers, right? That ratio of delta second to delta first with shear deformations included is going to be larger because we get more deformation out of the structure. By including shear deformations, we inherently make the structure more flexible. And so that ratio of delta second over delta first goes from 1.098 with shear deformation suppressed to 1.144 with shear deformations included. And then you can look at this as in a tabular format where each row in this table represents one iteration through that series of hand calculations. Excuse me. All right, so as we go through here and look at this, so here's the second order moment, the first order moment, 3600 is the first order moment in every case. And then that second order moment, you could say that this converges. I don't know if you would call this the first iteration. Maybe that's the 0th iteration, second, third, fourth. So this converges after about 3 or 4 iterations. So that's a nice stable problem. And if we were to look at these results graphically, then oftentimes we look at it like this, where we're plotting some deformation delta as the independent parameter and some load P. And so this represents the first iteration here. This represents the second iteration. That represents the third iteration. And so what you can see is the delta that you get on each of these iterations is diminishing to the point where it eventually becomes small enough that we can ignore it. And if we were to superimpose on top of this the true solution, then that might be the actual true solution to the problem. As you're applying the gravity load and the horizontal force, then this is the path that it would follow. But I just said something that's important. What we did was, we assumed that the horizontal force and the gravity load were applied at the same time. Maybe they're not. Maybe they're applied independently. Maybe you put the 200 kip force on in its entirety and then apply the horizontal load. And you might end up with a different set of results by applying them sequentially as opposed to applying them concurrently. All right, so the solution strategy, one solution strategy is to apply a little bit of the load incrementally. And so instead of applying the entirety of the 200 kip vertical force and the 20 kip horizontal force, maybe we apply a little bit at a time. Maybe we break that up into 10 increments. So we apply 20 kips vertically and 2 kips horizontally in each one of the increments. And then we can track the solution as we go along. And so what we can do is we can break the increment size down into smaller and smaller increments until we get to a case where the solution from 2 successive analyses converges with each other. And so I'll show that here. Here is the load applied incrementally. And so each one of these is basically a straight line, where in this case, I've broken it down into 1, 2, whoops, that's not a 2. 1, 2, 3, 4, 5, 6 increments. And so I'm basically applying 200 divided by 6 for the vertical in each one of those load increments. And so this is the analytical solution that I'm getting. And then this is the true solution to the structure. And so what you do then is you go in and you make that increment size smaller and smaller. You break it up into a larger and larger number of increments. until you get a convergence in the response of the structure between two different increments. And so if I go and do that with this particular problem, here is where I apply all of the load at once and just do one iteration with one increment. Here I break it down into 4 increments with one iteration at every increment. Here's a case where I break it down into 10 increments with one iteration at every increment. And what you can see is that as I increase the number of increments used in the solution, the responses tend to converge. And so you could say that probably most people would agree that the yellow line is close enough to the true solution that we could use that for our design purposes. And so you could say that this is converged at 10 increments. But again, it's kind of ridiculous because you had to solve the 100 increment problem in order to know that the 10 increment problem was satisfactory, right? So, all right. Now, if we look at the math behind that, it looks like that. So the delta divided by delta first ends up being, 1 in the first case, 1.065 in the second case, 1.098 with 10 increments, et cetera, et cetera. All right, and if we go through and look at the numbers behind that process, here they are in case you wanted to try and replicate that. Now, in that last exercise, I was going through and I was using a variable number of increments, but I was always going through with just one iteration at every load increment. I would apply, say, 10 kips vertically and 1 kip horizontally, and then I would just go through that series of calculations one time. I wouldn't iterate until I converged at every increment. You can combine the two processes. You can actually go through and break the problem up into a number of increments, and then during every increment, iterate until you get convergence. And so that is called the Newton-Raphson solution strategy. And you can see that illustrated here. So I've broken the problem up here conceptually into 2 increments. Here's the first increment, here's the second increment. And then through each one of these, I have, I'll use letters here. I have iteration A, iteration B, iteration C, and iteration D. So I have 4 iterations in that first increment. And then I have 1, 2, 3, looks like 4 iterations in that second increment. So if you combine an incremental solution with an iterative solution, you end up with something that's called the Newton-Raphson solution strategy. Now, this process is interesting because, let me erase this. If we go in and look at the increment, the iterations at each increment, the slope of these lines is each different. So if we were to go through and solve this using a matrix approach, then what we would have to do is recalculate the stiffness of our structure for every iteration within each increment. So we would have to recalculate the stiffness matrix 1, 2, 3, 4 times, 5, 6, 7, 8 times. And that assembly process, the calculation of the structure stiffness is costly in terms of time or computational resources. So that can be efficient, that can work out to give you a nice solution strategy, but it can be cost prohibitive as well. A modified version of the Newton-Raphson procedure is one where you only calculate that stiffness matrix or the structure stiffness once for every increment, and then use that same stiffness for every iteration within an increment. So here you can see I've got 1, 2, 3, 4, 5, 6 iterations for the first increment, which might seem initially like it's going to take more time, but you actually only have to calculate the stiffness once. So you iterate more times, but you save time because you only calculate the structure stiffness one time. And then up here with the second increment, we calculate a new stiffness. And what you can see is that each one of these lines has the same slope to it. So here we've gone from, 4 iterations in the second increment for the full Newton-Raphson, and now we're going to go with 1, 2, 3, 4, 5, 6, 7, maybe as many as 10 iterations in the second increment for the modified Newton-Raphson. So sometimes it works out to be more efficient from a time point of view, sometimes it doesn't. All right, now when you go in and look at SAP 2000, it uses a procedure that's based on the Newton-Raphson solution procedure. If you go to a more sophisticated package like Abacus or ANSYS or something like that, then you can actually use different solution processes. You can use an arc length method. You could use all kinds of different, and that's really Dr. Rosati's bailiwick. He's our resident expert on that type of analysis. Him and Dr. Zong as well. Quanxi Zong is also an analyst, and so if you wanted to pick their brains, they would have much more knowledge about that than I do. All right, now let's introduce another concept. We're going to go back and look at that problem again, except that now instead of looking at a single member, I'm going to look at a portal frame. And this portal frame is conceived conspicuously so that one member is resisting all of the horizontal force. So we have our original member AB, but now I'm going to add a second column, column CD. Column AB is fixed at its base, but column CD is pinned at the base. So if we go through and do an analysis of this, we're going to refer to column AB as the stability column or the side sway column because it's the only column in this frame that's resisting the horizontal force H. We're going to refer to column CD on the right as a gravity column. And the reason why is because the only thing that it's doing is resisting the gravity load Q that's applied to it. So when we looked at the Tower of Terror, we broke down the framing. Some of the columns were participating in the lateral force systems. Some of the columns were not. The columns that were participating in either the moment frames or the brace frames are referred to as stability columns. The other columns are there just to resist gravity loads, so they're called gravity columns. All right, so with that, let's go ahead and look at what happens when we apply a load to this. We end up with member AB resisting all of the horizontal force H. It's carrying all of the gravity load P, and then member CD is carrying all of the gravity load Q. Or at least that's what it looks like. What happens if we break this apart and look at equilibrium internally? Let's take a free body diagram of that gravity column, member CD. And if we look at that in just that column, what we find is that in order for it to be in equilibrium, it has to have some horizontal force coming through that strut, BD, in the top. If there wasn't that F sub H, that internal horizontal force in that member, column CD would just fall over to the right, right? It would be unstable. So now if we take a look at the moment at the base, we could say that that force, F sub H, has to be equal to Q times the horizontal displacement delta divided by the length of that column. Now, when we introduce equilibrium of the stability column, column AB, we have to represent that force acting with an equal magnitude, but in an opposite direction. So it works out that now if we consider equilibrium of the base of the stability column, that particular column, AB, sees second order effects not only from the load that's applied directly to it, load P, but it also sees second order effects from the loads that are applied to the gravity column. It also sees second order effects that are resulting from the load Q acting eccentrically through that horizontal displacement delta. And so because of this, column CD relies on column AB for its stability. So what we say is that column CD is a gravity column and it's leaning on the stability column, column AB. And so we refer to that column as a leaning column. And so the way that it works out is that, let me read this out loud so I get it right. Note that the column, this is the same moment at A that the column would experience is if it were carrying its own load plus the load that the leaning column is carrying, right? So, all right, now, if we go through and do our equilibrium iterations on this, then we include that force F sub H in there. Through our first iteration, we would get 3,600 kip inches. We would get a displacement of 1.342 inches. Okay, we can go through, let's see, yeah, so I'm going to skip that for now. We can go through a second iteration. We could calculate the moment at the base, including the horizontal force F sub H. Now look at the moment that's at the base of the column. We're already up well beyond what we had converged to in the absence of the leaning column. We had 3,900 kip inches. Now we're already at 4,100 kip inches. And we end up with a tip displacement or a story drift, if you will, of 1.592 inches. And we could go through this process and iterate until we converge. And what you would find is that we end up with a ratio of delta second over delta first that is far larger than what we got for just the stability column by itself. And so the takeaway from this is, with this being so large, whoops, I hit the erase button. Going to make a really good point, and then I blew it by, yeah, now I'm making it worse. There we go. That number was 1.12 when we looked at just the stability column alone, but by including the gravity framing in our second order analysis, we see that the gravity framing contributes significantly to the second order effects in our problem. And so when we go through and look at the single bay example and compare our hand calcs with the results from SAP 2000, you can see that we get similar results there. If we include shear deformations, this must be with shear deformations included. I must have a typo there. I thought I had this as a clean presentation, but I guess I do not. You can see that our ratio of delta second over delta first gets pretty large. So we're up in the order of 25% increase in displacements, and correspondingly a 25% increase in member actions based on our second order results. All right, so what do we take away from this so far? Well, the first order results with and without leaners, the second order results with and without leaners, right? It's second order effects can be important. In this case, they add about 20% to the drifts and the moments from our lateral framing. And the leaning columns are important. The leaning columns don't affect our first order results at all, right? When you guys were working on homework number 7 due tomorrow, you didn't have to include the gravity framing in order to get the results of your member forces for the brace frames and the moment frames. If you're going to do a second order analysis, however, you do have to include those leaning columns. You have to include all of the gravity framing in the structure in one form or another. And in fact, if you go back and look at the Tower of Terror handout and look through the load calculations, I have an artificial column line, an ACL, if you will. And I have some leaning column loads that are included in that. And until now, you probably didn't know what they were for. And now you know that we need to include them. So, all right. So this is probably a good time to wrap up. We're near the end of our hour. And this is a convenient place in this presentation to stop. So I'll hang around for a few minutes if you guys have questions that you might want me to answer. Otherwise, our next scheduled meeting is next Thursday at 12:30. I'll have office hours on Wednesday around 1 or 1:15, depending on my faculty meeting, and then I'll have office hours again sometime on Thursday next week. So feel free to reach out to me in the meantime. If you have a question or something, drop me a text message, send me an email. Otherwise, I'll see you in office hours or in class.